So let's summarize the input-output model altogether. We saw an example of exactly how this works, but this could be done for any size matrix and for any kind of economy, depending on the information that you have. So in general, for an input-output model, recall that we have the input-output matrix, A, which again indicates how much is required for each sector to produce one amount of output, and this of course depends on the individual problem. X is the production matrix, which tells you how much is produced by each sector of the economy. And D is the demand matrix, which is the amount of material or amount of production that is demanded from each one of the sectors. And finally, I put all these together to form a simple matrix equation. X minus AX is equal to D. Again, each constituent part here is a matrix. Moreover, this difference here tells me the net production in the economy, right? Given all these sectors, this tells me how much is produced, given that you've taken into account that some of the production is consumed by the production process itself. And so when I've done that, that's the net produced. And that should at least equal the demand, right? The demand for that particular product. If it's agricultural products, for food, for example, your populace has to demand a certain amount of food, and so you need to produce so much of each one of the parts of the economy in order to reach that particular level of food, right? Because of course, agriculture, as we saw a minute ago, depends on all the other sectors as well for inputs, right? It requires all these things, okay? So this again can be used very effectively to come up with policy ideas of how one might conduct an economy and how you might expect or estimate what the overall GDP each given year of an economy might be, whether you have growth or so on. So to solve this kind of thing, what we do is we employ all of the methods that we've learned previously for matrices and for matrix equations. And in fact, this general procedure works for all input-output models, no matter the size of each one of these matrices. So in particular, let's go ahead and solve this thing. We see that in general, what we want to do is we want to first factor out this x. So I'm left with identity minus a multiplied by x is d. We multiply both sides by the inverse of I minus a so that I isolate my unknown x, and we know already how to come up with inverses of matrices. Recall that again, I minus a is the same size as a. It's a new matrix, some n by n matrix. So I multiply both sides by the inverse of that matrix. When I do that, I wipe away this stuff in front of the x, so I just get an identity. The identity is the same size as a, and so I get the identity multiplied by x, which is my unknown, and that's equal to this I minus a inverse multiplied by d. And this really gives me the solution, right? This is going to give me just the simple column matrix x back again. This is like a 1. And the result is going to be another column matrix that we saw a minute ago, which is going to give me the solution, or the amount that I need to produce, right? But this is the relationship between the production, the input-output, and the demand. And certainly you could ask several different kinds of questions. Maybe A is unknown, but the other matrices are known, and so on and so forth, right? But the point is that this basic model, it's very simple, is very, very powerful because of its simplicity and because of the questions that it's able to answer. Okay, so this is, again, the overall idea of the input-output model.